that it's there. Can we see it more visually? Yes, we can. And so let me lead you through how we can do this. So here is an observer. It could be an eye, it could be a telescope. And suppose there's a galaxy out here in the universe. How do we see that galaxy? A ray of light leaves the galaxy and travels through the universe for perhaps billions of years before it enters the telescope or your eye. Now, how do we deduce where the galaxy is? Well, we deduce it by the direction that the ray is traveling as it enters our eye, right? We say the ray of light came this way, the galaxy must be there. Okay. Now, suppose I put in the middle a cluster of galaxies, and don't forget the dark matter. Okay. Now, if we consider a different ray of light, one going off like this, we now need to take into account what Einstein predicted when he developed general relativity. And that was that the gravitational field, due to mass, will deflect not only the trajectory of particles, but will deflect light itself. So this light ray will not continue in a straight line, but would rather bend and could end up going into our eye. Where will this observer see the galaxy? You can respond. Up, right. We extrapolate backwards and say the galaxy is up here. Is there any other ray of light that could make it into the observer's eye from that galaxy? Yes, great. I see people going down like this. So a ray of light could go down, be bent, up into the observer's eye, and the observer sees a ray of light here. Now take into account the fact that we live in a three-dimensional universe, okay, three-dimensional space. Are there any other rays of light that could make it into the eye? Yes, the rays would lie on I like to see, on a cone. So there's a whole rays of light on a cone that will all be bent by that cluster and make it into the observer's eye. If there's a cone of light coming into my eye, what do I see? A circle, a ring. It's called an Einstein ring. Einstein predicted that, okay? Now, it'll only be a perfect ring if the source, the deflector, and the eyeball in this case, are all in a perfectly straight line. If they're slightly skewed, we'll see a different image. Now, you can do an experiment tonight over the reception, okay, to figure out what that image will look like, because it turns out that there is a kind of lens that we can devise that has the right shape to produce this kind of effect. We call this gravitational lensing. And so this is your instrument, okay? But ignore the top part. It's the base that I want you to concentrate, okay? So actually at home, whenever we break a wine glass, I save the bottom, take it over to the machine shop, we shave it off, and I have a little gravitational lens, okay? So it's got the right shape to produce the lensing. And so the next thing you need to do in your experiment is grab a napkin. I grabbed a piece of graph paper. I'm a physicist, so. A napkin, draw a little model galaxy in the middle, and now put the lens over the galaxy, and what you'll find is that you will see a ring, an Einstein ring. Now move the base off to the side, and the ring will split up into arcs, okay? And you can put it on top of any image on the graph paper. You can see how all the lines on the graph paper have been distorted. And again, this is a kind of an accurate model of what happens with the gravitational lensing. Okay, so the question is, do we see this in the sky? Do we see arcs in the sky when we look at, say, a cluster of galaxies? And the answer is yes. And so here's an image from the Hubble Space Telescope. Many of the images you were seeing earlier were from the Hubble Space Telescope. Well, first of all, the golden-shaped galaxies, those are the galaxies in the cluster. They're the ones that are embedded in that sea of dark matter that are causing the bending of the light